Good evening, Southport. For the last 15-20 minutes or so, we've been watching cosmic rays. And I am going to switch from the camera that's looking at this cloud chamber, which I'll explain in due course in a little while. I'm going to switch back to good old-fashioned PowerPoint and give you a talk about cosmic rays, and we'll be jumping backwards and forwards between some of the demonstrations on this front table in due course. So I'm going to be telling you a little bit, after a brief introduction, I'll be telling you about some of how we define background radiation. Before talking about what radiation is coming from the universe, it helps to put it in context by talking about what radiation is around us all the time anyway, terrestrial radiation. Then I'll be talking about cosmic rays, how they were discovered 100 or so years ago. Then I'll be having a quick look at how we can detect cosmic rays. One way is using a cloud chamber. And then I'll be finishing by asking, well, where do they come from? In other words, we're working backwards. We're looking at them, thinking about what's actually happening, and then asking, well, where do they come from in the first place? And then I'll summarize right at the end. So the U3A lawyers require me to say the following, and that is that this is a demonstration which includes not only a cloud chamber, which is perfectly safe, I have a Geiger counter, and I have a small number of radioactive samples. Now, these radioactive samples pose no risk to you, but once the demonstrations are done, I'm going to put the radioactive samples away and take them out of harm's way, and then you're free to approach the bench more closely if you want to take a close gander of what it is that we've got on this front table. So what I've got here is a couple of different types of detector. One which is what everybody calls a Geiger counter, and we'll see how that's useful later. And also we have this cloud chamber, which is something I built on my kitchen table a few months back and have been using for the last few months to demonstrate cosmic rays and to demonstrate how we can see radioactivity. So let me start with switching on the Geiger counter. Let me just turn the camera so you can see it a little more clearly. Switch back to the video for the second. On the front here we have a Geiger counter. It's clicking. It's clicking because it's picking up something. It's picking up some activity. Some particles, some subatomic particles are passing through the Geiger counter. You can hear how many. Not many. 1 a second, 2 a second, 1 every 2 seconds. That's normal background radiation. So the question we can ask is, well, what is producing those clicks in the sense of what particles are we actually picking up? So each click signals the arrival of something, a subatomic particle of some kind passing through what everybody tends to call a Geiger counter. Physicists don't like that. Physicists prefer to give it its correct name of a Geiger-Müller detector, because that recognizes both Geiger and Müller as the inventors of this technology. But everybody calls them Geiger counters, so we're going to stick to that for this particular talk. So we're listening to lots of clicks, or at least a few clicks per second. What are the clicks? They're the arrival of some particle. Where did the particle come from? Well, maybe it was spat out of an atom lurking somewhere in this room. There are some atoms in this room that are radioactive and are producing things which could produce a click in the Geiger counter. It's also possible that the origins of these clicks are particles coming from an origin much, much further away, possibly a galaxy. Long, long ago, in a galaxy far, far away, maybe, some supernova, some black hole produced a very energetic charged particle, and we're now hearing those clicks. The bottom line is a Geiger counter doesn't help us. A Geiger counter literally just counts clicks. It just says lots of clicks are coming in. A Geiger counter does not tell us what those clicks are. If we want to know what the clicks are, we need a different type of detector, which I will come to in due course. So before we talk about cosmic rays proper, let's talk about background radiation. So remember, radiation, although some people are frightened of that word, radiation is around us all of the time. Every day, basically every day of your life, you've been subjected to some sort of radiation. Because you have to remember that we live on a radioactive planet. You don't tend to think of that. Radioactive doesn't mean man-made. Radioactive means it is active, it is changing. Certain elements will change into other elements. The Earth was radioactive when it was made 4.5 billion years ago, and it's radioactive today. It's a natural consequence of how elements behave. If we look at the periodic table, where we take all the elements that we know of that exist on the Earth or elsewhere in the solar system and lay them out, we get an idea of the various properties of various elements. And we have come to the conclusion, by studying them for 100 years or more, that some atoms are stable. In other words, if you make an atom, that atom essentially does not change for its entire life, as far as we can tell, ever. If you make a certain atom and it's stable, it might be that you can take an electron away or add an electron to it and you can do chemistry, but that atom is essentially the same atom. So some atoms are unchanged forever. But we can recognize that some atoms in the periodic table are unstable. They're not happy being what they are. They want to change. Physicists call it decay. Decay from one element into another element. So what we're saying is some elements can change into another element. If we have an atom of radium, it might decide it doesn't want to be radium and changes into an atom of lead, for instance. And what happens when we have a change from one element to another is the nucleus of the atom spits out something, some subatomic particles. And we can visualize that by having a look at what's going on with, let's just take an example. Let's take one atom in the periodic table. Let's take uranium. So we're now going to switch back to the video. I intend at this point to show a piece of uranium, and I've got more than one piece of uranium here. One of the pieces of uranium I have is embedded in a piece of glass. So this is uranium glass. I'm not sure if anybody's ever come across this stuff. Is it recognizable to anybody? Some people collect uranium glass. It's glass in which there is some uranium. We know it's radioactive because if we place it in front of the Geiger counter, maybe if I use my other hand so you can still see the dial rather than blocking that, you can see that we get a higher number of counts than just background radiation. And that's now getting annoying, so let me switch the speaker off.
Was the uranium used to colour the glass?
One of the reasons you put uranium in glass is because it gives a nice colour, and some people say that looks pretty. But the main reason people put uranium in glass is not to make it radioactive, it's to make it look pretty, because if you put it into a cabinet and shine UV on it, it fluoresces like mad. So people put this in display cabinets and then put UV lights around the edge, and then you see the whole thing light up. So it can be spectacular. But that's just a side effect of having uranium. And you could argue the radioactivity is also a side effect. But we can't see the radiation being produced by that. We heard the clicks on the Geiger counter, but this, unfortunately, is too big to go in my cloud chamber. So we're not going to be using that. And just for anybody that happens to be looking at the video, I have just demonstrated to the audience that uranium glass, when subjected to UV, fluoresces like mad. So that was the point of that particular demonstration. But I'm not going to use that particular sample just because it is too big. I'm going to pick a tiny piece of mineral which has some uranium in it. And I'm going to take this tiny piece of uranium. It's barely a few millimeters in size, but it is quite definitely radioactive because even though it's only a few millimeters in size, I've switched the speaker off, but you can see the counts per second goes up quite considerably when I place it in front of the Geiger counter. If I just put it back on temporarily, that is quite definitely a piece of uranium. What I'm going to do is to go back to my cloud chamber where we were looking at cosmic rays earlier and ask what happens if I put a radioactive sample in the cloud chamber. Does it allow us to see the radiation coming out of this particular sample? I'm going to try and do this with minimal disturbance to the cloud chamber. The cloud chamber relies on having hot at the top, cold at the bottom, and the alcohol basically drifts slowly down, forming clouds, and any charged particle that passes through the cloud chamber might leave a contrail, much like an aircraft flying high through the atmosphere might leave a contrail of water behind it because the water is in the atmosphere, but the passing aircraft makes the water condense and leaves a white contrail behind it. The same is true for a radioactive sample. It might take a minute or so to settle down, but now I hope you can see that that radioactive sample is doing something. We still, in principle, are seeing cosmic rays, but now I think you can see that rather more than just the occasional cosmic ray, we are seeing lots of lines that are coming out of the sample. And once we have let it settle for a minute or so, we now see multiple lines per second coming out of the sample. Notice that all of those lines, pretty much all of the lines, originate from the sample. So it's no surprise that we interpret that to mean the sample is kicking out something. Something is coming out of that radioactive sample, forming these tracks. Anything that comes up, we don't see. Anything that goes down, we don't see. Anything that comes out sideways, we have a chance of seeing it in the cloud chamber by the formation of these tracks. If we watch it just for a minute or so, we might notice that some of the tracks are relatively bright and relatively narrow and quite straight. Notice that every once in a while we get a rather more fuzzy track. Maybe if we just watch it for a moment, there was a couple going off to the left, a bright one there, a narrow one. Sometimes it's a little difficult to see, but once you've seen a few of them, your eye tends to get used to the idea of, yeah, that one was narrow and bright, that one was a little fuzzier and broader. So that tells us that this particular element, uranium, and indeed many other radioactive elements that want to change from something into something else, are kicking out small subatomic particles. Let me switch back to the PowerPoint. This is a video I made earlier in Blue Peter fashion, just in case there was any glitch. In other words, if I dropped the case that this came in and it smashed and I didn't have a cloud chamber to show you, here's a picture of a much bigger sample in the same cloud chamber that I took on my kitchen table. And again, I hope you can see that there's lots of tracks coming out of this thing. Some of them are very bright and narrow, and some of them are very broad. I took a video of 1 or 2 minutes or something like that, and then I just sat down with that video and picked out the frames that showed the most interesting looking tracks, and then just added all of those frames together. So that is, if you like, a time lapse of lots of things coming out of that particular rock. And this, I hope, makes it even clearer. Some of those tracks are very narrow, barely a pixel or so wide, and some of them are very broad and very ghostly. So it's clear that the rock, the radioactive rock, is emitting something, and it's clear that some particles are leaving tracks in the detector, but what are they? Well, about 100 years of research have given us a clue as to what's actually going on. We know atoms look a little bit like this. That's not a particularly fantastic representation of an atom, but it's good enough for what we need to know. An atom is a positively charged nucleus and lots of negatively charged electrons buzzing around like bees. But we know that when one atom changes to another atom, when one element changes to another element, like when uranium decides it doesn't like being uranium anymore and wants to change into something else, it's the nucleus that spits out some radiation. It's nothing to do with the electrons that are buzzing around. It might be the electron spits out, sorry, it might be that the nucleus spits out some particles, including electrons, but it's not these electrons buzzing around that we're interested in. It's what's going on in that central nucleus alone. And although that looks a little bit complicated, this is just to make the point that if we have a very heavy nucleus like uranium, it's a big bag of protons and neutrons. And what can a nucleus spit out? Well, in principle, a nucleus might spit out a lot of different things. A nucleus might spit out a proton. If it wants to be a little bit lighter, it might decide to get rid of some of its positive charge. It might decide to spit out a neutron. A neutron is a neutrally charged particle, and it might get rid of it to make the nucleus more stable. It might decide to spit out more than one particle at a time. It might decide to spit out 2 protons and 2 neutrons, for reasons I'm not going to go into, but that's a very stable structure. 2 protons plus 2 neutrons is what we call an alpha particle. So an unstable nucleus might decide to spit out an alpha particle. It also might decide to spit out an electron, or rather oddly, an antimatter equivalent of the electron. It looks like an electron, but it's got the opposite electrical charge. We call that an anti-electron, or sometimes we call that a positron. And it's also possible that a nucleus might spit out a gamma ray. So all of these things were studied 100 or so years ago, and of all of these possibilities, we're not going to think about all of these possibilities. We're just going to remind ourselves about the most common ones, which are labeled the alpha and the beta and the gamma particle, sometimes called alpha and beta and gamma rays. It doesn't really matter whether you're talking about a ray or a particle. In fundamental physics, you sort of treat them as the same thing. The early days, they tended to be called rays because they didn't know what they were. Now we tend to more likely call them particles, but it doesn't really matter. A beta ray is the same thing as a beta particle. An alpha ray is the same thing as an alpha particle. So alphas, that's just a shortcut, meaning these particles are relatively heavy. They're made of 4 so-called nucleons, 2 protons and 2 neutrons, so they're quite big, quite heavy, and they've got a lot of electrical charge. Betas is the label we give for those things that are either electrons or their antimatter equivalent, if you like, positive electrons or negative electrons. So they're much lighter because an electron is much lighter than a proton, and an alpha, remember, is 2 protons and 2 neutrons, so that's much heavier overall. Gamma is a little different because a gamma is an electromagnetic wave. It's not a particle in the same sense that an alpha ray or a beta ray is. A gamma ray is an electromagnetic wave. And as it happens, they don't show up in cloud chambers, but they do produce clicks in Geiger counters. So that's the alpha and the beta and the gamma. There are other ways that a nucleus can change, but we're not going to be thinking about those this evening. So if we go back to our video, when we're looking at what's actually going on there, we can now start to think about what it is that it's actually producing. Don't tell me it's now stopped. It's just settling down. No, it's it's fine. Given that these things appear at random, sometimes you get nothing for a few seconds and then a whole load come out. But whenever we have a very narrow track, that tells us that this is an electron, a very lightweight particle that produces a very small track, whereas an alpha particle, remember that's the big, massive particle, 2 protons and 2 neutrons, that's like a bulldozer. And when it goes through the cloud chamber, it produces quite a substantial disturbance to the cloud chamber and produces a much broader track through the system. So I'm going to switch back just to remind us in, again, Blue Peter fashion. There's one that I did earlier. And again, if I switch to actually showing the result of adding together these tracks by taking a video and then adding the frames together, everything that is a nice, very well-defined bright track, that is a beta. It's either an electron or possibly an anti-electron, an antimatter equivalent of that electron. Whereas the much broader ones that we can see here, the more ghostly tracks, they are the alpha particles, the bulldozers that are producing a much wider track as they go through the medium. And before I forget, I'm going to do this off camera, but I'm going to take the sample out of the cloud chamber because later I want to go back to cosmic rays, and I don't want that particle there. So I'll put that back in its box. And also I'll be able to put this to one side, and then all radioactive materials will have been removed from the front bench. Okay. So, just as a point of definition, because I'll be using this word later, just a definition of what I mean by a radioactive isotope. Some atoms are sort of cousins of each other in the sense that they have the same number of protons, so a particular atom is defined by how many protons, how much positive charge is in the nucleus. So for instance, all carbon atoms have 6 protons in the nucleus as a matter of definition. In other words, if you take a collection of protons and neutrons, if you count the protons, if the answer is 6, that is what we call carbon. Carbon is simply the label we use for a nucleus which has 6 protons in the nucleus. But the number of neutrons might be variable, so this is still carbon regardless of how many neutrons we have. If we have a carbon atom that has 6 neutrons in the nucleus, the total number of protons plus neutrons is 6 plus 6, 12. We call that isotope carbon 12. but carbon comes in different varieties, different cousins of carbon, different isotopes of carbon. So a carbon atom that has 8 neutrons in the nucleus, still with those 6 protons because it's still carbon, that would be a total number of 6 protons plus 8 neutrons equals 14 in total. We call that carbon-14. That's the nucleus we use for carbon dating. It's one of the isotopes of carbon. It's useful for carbon dating because carbon-14 wants to change into something else. Carbon-12 is mainly what you're made of. You're made of a huge amount of carbon-12, which is stable. A little bit of you is carbon-14, which wants to change in something else. That's how we can tell how old a tree, for instance, is by carbon dating it and looking at how much carbon-14 there is in a particular sample of a particular carbon-bearing material, like a tree or an animal. So, in terms of the most likely radioactive elements you're ever going to come across, it's perhaps surprising to realize that one of them is probably one you've already heard of, potassium. Your body contains a fair bit of potassium, and yet potassium is actually one of the most abundant of the radioactive elements. There's a lot of it in your body, simply because it's part of the essential workings of life. If you work out how many atoms of potassium there are in your body and how likely they are to change into something else, actually there are 4,000 every second in your body. 4,000 potassium atoms are changing into something else every second. But you have an awful lot of atoms, so 4,000 per second doesn't change you that much. It's one of the largest contributions to background radiation because we're all made, to some extent, of a little bit of potassium. There's a few grams of potassium in everybody. The other elements that are contributing to background radiation on the Earth are thorium, which is more abundant than uranium, even though you've probably heard of uranium and you might not have heard of thorium. Thorium is more abundant than uranium, and uranium is more abundant than you think. Uranium is actually more abundant by a factor of 500 compared to gold. There's 3 parts per million. That is way more than the amount of gold in the Earth. But it's a little more difficult to dig out, so we don't tend to have lots of it lying around compared to the economic benefit of going out and digging up a whole load of gold. In the Earth's core, the core of the Earth is being kept warm by a lot of radioactive elements. These 3 amongst them are keeping the Earth's core molten from the amount of heat generated by all that radioactive decay. The core of the Earth is not being kept warm because the sun is shining on the Earth. That's nothing to do with it. The molten Earth's core is being kept molten by radioactive decay of these elements that have been around for billions of years. And because the Earth's core is molten, we have a rotating metal core, and that's a dynamo which is generating for us a magnetic field. So our magnetic field of the Earth has been around for billions of years because we have a molten core. And it's an interesting sort of cycle of life that to some extent the Earth's magnetic field protects us from some radiation outside the Earth, and the protective magnetic field is generated itself by radiation inside the Earth. And we think that maybe that's why Mars is the way it is. Mars doesn't have a molten core because it's cold, it's smaller, and it must have cooled off earlier, and maybe its core solidified a long time ago, so it doesn't have a molten core. If it doesn't have a molten core, it doesn't have a magnetic field. If it doesn't have a magnetic field, it doesn't have the same protection against radiation from outside the planet, and maybe that's what stripped Mars of its atmosphere. So we should be thankful for the radioactive elements in the core of the Earth giving us a magnetic field, protecting us. And just as a little bit of an aside, I said that potassium produces radiation. I also said earlier that different cousins, different isotopes of atoms exist. It just so happens that potassium has a radioactive isotope. So of all the potassium in your body, there is a particular isotope with a particular number of protons and neutrons that add up to 40. So this isotope is called potassium-40, and it emits beta plus radiation. Beta, remember, is an electron type thing, but beta plus means it's got the opposite charge to an electron. So in fact, potassium-40 actually emits anti-electrons, not electrons. It's the antimatter equivalent of electrons. So any body, i.e. you, or any food that's rich in potassium, like Brazil nuts or bananas, for instance, generates antimatter. It's spitting out antimatter, not a great deal of it, but a little bit of antimatter is generated by bananas. And that actually gave rise to the so-called unit of the banana equivalent dose. So rather than talking about rads and rems and all these things that people can't make sense of, rather than having a strict physical definition, why don't you just compare the amount of radiation you're talking about to the amount of radiation that comes out of a banana, and hence the banana equivalent dose. It only works for relatively low levels of radiation. It doesn't work for a Fukushima accident or Chernobyl sort of thing. But you can, if you wish, compare the amount of radiation to the amount of radiation you would receive if you ate a banana. And just out of interest, just as an aside, if one banana is represented by that, you can ask, well, cosmic rays are raining down on the Earth all the time. We've seen a few of them earlier. So how many cosmic rays are going through you? What's the total dose, the total radiation dose to you every day compared to eating one banana? And the answer is the dose of cosmic rays is equivalent to about 10 bananas. Actually, it would be a little more if you fly a lot, because if you fly a lot, you're at elevated altitude, you tend to receive a higher radiation dose of cosmic rays. But that's just a way of sort of relating things to something that's relatable, rather than saying it's this many rads or this many rems or this many sieverts, all these units that in principle you can use but don't mean anything to anybody other than physicists. And so the banana equivalent dose is just a way of bringing it back down to Earth, as it were. And let me finish this section with just saying not all radioactive materials are necessarily little chunks of uranium, little pieces of rock. There are some that are like that, but there are actually some radioactive samples that are gases. So radon is the most famous of those. It's a radioactive gas formed by the radioactive decay of the little bits of uranium that exist in rock. In other words, underneath our feet, there's a tiny amount of uranium. It's not economical to dig it out of the ground, so there's so little of it. But uranium often exists where there is particular igneous rock, like granite, for instance. And that means there's an awful lot of radon produced in parts of the UK that are rich in granite. And here the map shows you in red where most of the radon is produced. And if you follow it through, you can see, well, these areas are where you have mountains, or at least hill ranges. You have the Pennines, you have the Cornwall and Devon, for instance, you have Cambria and Cumbria. And that means that if we were to put this cloud chamber in Cornwall, we would actually see more tracks produced by radon than we would see here. If you look at where we are in the map of England, the blue colour means not much. And you can see that in this part of the northwest and in various parts of the West Midlands, there's not an awful lot of granite around, and so there's not an awful lot of radon. If we were to see radon, if the radon levels were higher, what would we see? Well, radon emits alphas, these bulldozers. We would see more of these fainter trails compared to, for instance, the electron trails that we see in radioactive materials. I'm curious to know, if you did take one of these down to Cornwall, how much difference would it actually make? One day perhaps I'll actually try and find out. But even here, where we don't have much granite, there is still radon in this room, simply because there is uranium around somewhere. I tried to calculate that, and I reckon the total number of radon atoms in this room is probably about 1 billion. And if that sounds scary, remember it's tiny compared to the number of oxygen and nitrogen atoms in this room, which is 1 million, million, or something like that. So 1 billion radon atoms is actually a tiny, 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 tiny fraction of what's going on in here. But occasionally we might see something in the cloud chamber which tells us we've seen an alpha particle from radon. Okay, so that's the background to give us some sort of context to thinking about radiation and radioactivity. So now let's talk proper about cosmic rays. So cosmic rays, when did investigations of radiation really kick off? You might have heard of some of these pioneers of radiation. You've all heard of Marie Curie, yep. Some of you might have heard of Becquerel. Quite possibly, maybe none of you have heard of Hess, who knows. but these were all pioneers in their own right. Becquerel effectively discovered radioactivity. He saw that his photographic plates got fogged if he happened to leave a piece of pitchblende, a uranium ore, close by. Even though the photographic plate was sealed inside light-tight container, it still got fogged if he brought a radioactive material too close. Something was fogging his radioactive plates. That was the discovery of radiation. Marie Curie, I'm sure you all know, developed the way of purifying various radioactive elements such as polonium, radium, etc. Victor Hess's story is perhaps not so well known. But in the latter part of the 1800s, towards the 1900s, it was known that electroscopes would discharge. An electroscope, as indicated on the right, is a very simple device. It's just a couple of gold leaves in a sort of bell jar to try and avoid any breeze affecting the result. If you charge this up by putting a charge on the top, like charges repel, remember. So if you've got two very lightweight pieces of gold leaf, that's chosen because they are very lightweight, very thin. If they're both positively charged or both negatively charged, they will repel each other, and so the gold leaves will separate. So it's a way of measuring charge. But it was observed at the turn of the century that when they charged up one of these electroscopes by rubbing themselves on a cat or a balloon or something else and producing a little bit of charge, they noticed that the gold leaves would slowly collapse, indicating that charge is being added or taken away from these electroscopes. Why do they discharge? Some external radiation, some so-called background radiation, is affecting these electroscopes. So how can you figure out what's going on? Is this background radiation that's discharging these electroscopes, is it coming from above, from the sky, or is it coming from below, the ground? That was not known at the turn of the century. In 1910, a physicist called Theodore Wolff took an electroscope to the top of the Eiffel Tower. He measured how fast it discharges at the bottom, and then he took that same electroscope to the top and did the same experiment to see, can you see a difference as a function of height? And he sort of said, well, there's a difference, but it's not very convincing. The radiation levels decreased somewhat, but far less than you'd expect if the radiation was coming from the ground. So what does that mean? Does it mean it's coming from above? How do you know it's not coming from the tower itself? How do you know it's not coming from the atmosphere? At this point, the existence of radon was known. So how can you get rid of the factor that radon is all around us and might be influencing your experiments? And asking, is Eiffel Tower radioactive, is not a silly thing to think about. The Eiffel Tower is made of iron. Iron is dug out of the ground. The ground is radioactive, so perhaps the tower is radioactive. So how do we get around this dilemma of getting high enough to see whether or not it's the ground or the sky that's affecting the discharge of an electroscope? This is effectively where Hess came in. We had to try and figure out, is this background radiation, whatever it is, coming from above or from below? Hess figured correctly the Eiffel Tower is simply not high enough to make enough of a difference to reliably tell what's going on. So he figured, how do you get higher than the Eiffel Tower? At the time, there was only one way to do it, balloon flights. So basically in 1911, 1912, he basically designed himself some electroscopes or some detectors that were robust enough to survive going up in a hot air balloon. And in 1911, he took them up in a balloon to 1,000 meters, much higher than the Eiffel Tower. And he sort of couldn't really tell what was going on. It still wasn't high enough to get a definitive answer. Is it going up or is it going down? Which will tell you where the radiation is coming from. So he had some more flights, and in 1912, he went to 5,000 meters, and bam, the radiation levels went up significantly. So now it was clear, most of the radiation is coming from the sky, not from the ground. So yes, the ground will be radioactive, and if you happen to be living in a highly radioactive area, that might be influencing your results. But most radiation is coming from above. But was it from the sun, or was it from somewhere else? This was the next big question. It's coming from somewhere up there, not the Earth. If it's not coming from the Earth, is it coming from the sun? How can you tell? One option is, well, take your hot air balloon up at night. Do you really want to fly a hot air balloon at night where you can't see where you're going You're at the mercy of the winds, and you can't see where you're going to land. It's a crazy idea to take a hot air balloon up at night. That would have been the best way to show, is the sun an influence or not. You also have the problem that it will be colder at night, and will that make a difference? There's other factors that will change if you decide to wait until the following night. So he had a brilliant idea. You take a hot air balloon up and you measure the radiation levels, and you do it on a day where there's a total eclipse. Fantastic idea. You take it up, you measure the radiation, you wait for the moon to cover the sun, and you ask, does the radiation drop when the moon covers the sun? Surely whatever radiation we're talking about is not going to go through the moon. So as soon as you cover the disk of the sun, you should be stopping the radiation. He determined that the sun was not the source of radiation. In other words, it didn't make any difference if you take the data during a solar eclipse or not. The radiation is cosmic. It is coming from outside of the solar system. The sun is not the origin of, certainly not most. It might be partially responsible for some of the radiation, but most of it is coming from outside the solar system. In 1936, Hess was awarded the Nobel Prize for the discovery of cosmic radiation. The term cosmic rays and cosmic radiation cropped up in the 1920s, and he got the Nobel Prize for taking these historic balloon flights and showing what was going on. We now know something about what's happening. We know that particles are hitting the top of the atmosphere and producing a shower. There's this cascade, this avalanche. Something very energetic hits the top of the atmosphere and, like a pinball machine, collides with an atom of oxygen or an atom of nitrogen, more likely, and then that produces more particles, which then collide with more atoms, which then produces more particles, which produces more particles. And you get this sort of effect of this cascade, this avalanche of perhaps one. This artist's impression is not great because it sort of shows two happening at once, but just ignore the shower on the left. A single particle coming in from some source or another, which we'll discuss in due course, produces a shower of secondary particles, a so-called air shower. If the Earth didn't have an atmosphere, this wouldn't happen. It would just impact the surface. But because we have an atmosphere, this happens. This diagram on the right is a highly schematic version of what we're talking about. It shows an incoming, I still want to use the laser, it has an incoming primary cosmic ray, which produces so-called secondary particles that are generated. Here, the simplified diagram on the right simply shows a half a dozen different particles being generated by an incoming particle hitting the atmosphere. In practice, it is thousands, possibly even millions of particles that are generated if the incoming particle is energetic enough. That's because every time one particle generates 2 or 3, which then generates 6, which then generate 10, which then generate 30, the energy is spread over all of those additional particles. So each layer, if you like, of the avalanche, each layer of the shower, each particle shares the energy of the incoming original primary cosmic ray. So we get a cascade which might result in thousands or possibly even millions of secondary particles, and it's those secondary particles that reach ground level. The primary is the one that hits the atmosphere. The secondaries are the air shower that's produced, and that's what we're seeing in the cloud chamber here. What particles are these? Well, some of these particles are ones we know about. For instance, protons, which we know are part of the nucleus of every atom in your body. Some of these particles are electrons, which are part of the atoms in your body. But some of these particles are more exotic. Some of the particles that are generated in an air shower are nothing to do with how atoms are put together. For instance, a lot of them are so-called muons. Muons only live for a fraction of a second. So some of these particles are stable, like protons and electrons, but some of the particles being generated in a cosmic ray shower are unstable and only live for a tiny, tiny fraction of a second. Muons are one of the most abundant of these particles. What is a muon? As I say, nothing to do with atoms, but a muon is, in a sense, a heavy version of an electron. If we look at all of the particles that exist in the universe, a muon looks to all the world like an electron, but it's 200 times as massive. So it's a completely different particle, but it shares some of the characteristics of an electron, the same possibility of a positive or negative charge, and the same way that it interacts with other particles. So muons have no part to play in making atoms, but a lot of them are generated by cosmic ray showers. And a muon will only live for a couple of microseconds, a couple of millionths of a second or so. But a few microseconds is long enough for the particle to come from the high atmosphere through a cloud chamber, leave a trail, then it dies. A bit like a mayfly, doesn't last very long. And that's what a muon might look like if we looked at it in our cloud chamber. It would effectively be just a trail of droplets left by a muon, which would tend to be a relatively straight line. Electrons tend to look much more wiggly. Muons are very energetic and more massive, and they're not deflected by bouncing off the oxygen or nitrogen or anything else that's in the cloud chamber. So a muon tends to be energetic enough to leave a straight trail, whereas an electron leaves a rather wiggly trail. So we can tell the difference when we look in a cloud chamber. So secondary particles might be protons, electrons, muons, but what is it that actually hits the atmosphere in the first place? What are the primary particles that are generating these air showers? Well, various decades of research have told us that most of the particles that are impacting the Earth, producing these cosmic ray showers, are protons. So most of these incoming particles are nuclei of hydrogen atoms. A small number of them are alpha particles, which you can also think of, if you wish, as being the nuclei of helium atoms. So about 9% of cosmic rays are hitting the atmosphere. They are alpha particles. And notice that adds up to 99%. The remaining 1% is everything else we can think of. Perhaps a few electrons, perhaps nuclei of heavier atoms. Which atoms? Well, essentially, any atom that we see in the solar system could in principle be a cosmic ray. It could be carbon or nitrogen or oxygen or iron or lead or in principle anything. When you strip the electrons off, you're left with a positively charged nucleus. That's everything that comes into that 1%. So most are protons, some are alphas, 1% is everything else we can think of. That's what is hitting the top of our atmosphere. So how can we actually detect these cosmic rays? How can we detect either what's hitting the top of the atmosphere, or how can we detect the air shower that's produced arriving at ground level? Well, one way we can detect is with the Geiger counter that I showed you before. The Geiger counter, what is the actual detector itself, more correctly called the Geiger-Müller tube? Well, it's a tube in which we have some inert gas, maybe argon, maybe helium, and any radiation that comes in will ionize some of the atoms inside the tube, and by applying a big positive and negative voltage to the middle of the tube and a negative voltage to the outside, if we generate an ion by separating a positively charged nucleus from a negatively charged electron, then that large voltage difference will separate them, and our little yellow box there will detect that change in current, and the current is converted into a click. So we don't know what radiation ionized the atom. We simply allow the Geiger counter to count how many changes to current it sees, and hence how many clicks, and tell us there are this many particles passing through. There is this much level of radiation without specifying which it is. But in terms of the device that we were looking at earlier, the cloud chamber, that's an invention that's more than 100 years old now. Back in 1910 or 1911, a particularly enterprising physicist was on the top of Ben Nevis and saw the Brocken spectre. Anybody seen a Brocken spectre? Ah, right. If you're looking in a relatively moist area, or if you're inside a cloud and the sun is coming through from behind you, you might see your shadow and this sort of halo around it. So in 1894, Charles Wilson saw a Brocken spectre and thought, this is an interesting phenomena. I don't want to have to go to the top of Ben Nevis every time I want to study this phenomena. Is there something I can do in the laboratory to make myself a cloud in a box? Can I make clouds on demand so I can study things like the Brocken spectre, for instance? So that's the reasoning that he went with. He was simply interested in atmospheric phenomena. And in 1911, he perfected a cloud chamber in which he tried to make water vapor condense into clouds in the way that allowed him to study things like the Brocken spectre. But it wasn't too long when he was building his cloud chamber, he realized, well, I can sort of make clouds, but every once in a while I keep getting these damn trails coming through. What's going on? And then he realized he was looking at charged particles that were leaving contrails through his cloud chamber. They condensed the, in his case, water, in our case, alcohol. It condensed the vapor inside the cloud chamber and produced tiny droplets showing a track of where the particle had been. So for quite a long time, the cloud chamber was a phenomenally useful device for particle physicists. Particle physicists figured that atoms were made of protons and electrons, and we know about these other particles that we think exist, but now we can visualize them. Now we can actually say, if we bang these two things together in an accelerator and want to know what happens, we can visualize the particles that are produced, just like we can visualize the radioactivity that's coming out of a piece of uranium rock, for instance. So this was the mainstay of particle physics for quite a few decades after its invention in 1911. For quite a few decades, that was really important, which is why in 1927 he was awarded the Nobel Prize in Physics. And that quote is a wonderful one. The cloud chamber was described as the most original and wonderful instrument in scientific history. What a statement. That's how much that changed physics, by allowing us to see the subatomic. Up to that point, we had no way. We had ability to sort of count clicks, but now we can see the particles. We can see what they're doing. We can see how energetic they are. We can tell the difference of this particle to that particle. If we apply a magnetic field, we can see them bending this way or bending that way, which tells us it's got a positive charge or a negative charge. We can do all sorts of experiments as soon as we have a cloud chamber. So that was the original cloud chamber in 1911 on the left, and this is my version of it on the right. So I am not going to describe the details of how I built this beastie, but my cloud chamber is a very distant cousin of Wilson's. It benefits from 100 years of technology. So Wilson used water and he tried to make clouds. In this particular case, I'm using alcohol, and I'm just using a device which basically puts heat at the top, cold at the bottom, and a little sponge, a little cosmetic sponge, holds some alcohol, which allows me to make clouds and then see the tracks. So in effect, what we're really saying is, all we're really saying is that as long as we can put some alcohol into the device, keep the top at a modest temperature of about plus 35 centigrade or so. In other words, I don't need to keep it piping hot like this coaster is designed to do. And the bottom needs to be about minus 20, minus 25 Celsius. So it needs to be quite cold, but you can buy these refrigeration units from Amazon for about 15, 20 pounds or so. So I'm not going to describe how I built it, but you're welcome to come and have a closer look at it later if you so wish. But the cold plate at the bottom there, that black rectangle, is what we were looking at earlier, and that's where the tracks will form. So if we go back, hopefully the device, now that I've removed the uranium from the system, we're now back to seeing cosmic rays, and this will either cooperate or it won't, which means either we'll see nothing for the next 30 seconds and I will waffle until I see something, or maybe it won't cooperate. I think, let me just check. Yep, everything looks fine. We are definitely in the position of seeing the occasional cosmic ray, but I'm not going to wait here for 5 minutes waiting for one. If we haven't got one, we can always come back to it later. But basically, the idea of the cloud chamber was being able to visualize radioactivity and experiments carried out, particle accelerators, for instance, to see what's actually going on. So in this particular case, again, here's one I made earlier. Here's a video I made on my kitchen table of the same cloud chamber, and we can see various, sometimes they're very straight and very obvious, sometimes they're very ghostly. Every once in a while they look quite wiggly, indicating an electron. I can't remember how many tracks there are in this particular video. That was a nice one of an electron, something or other going through there. I'm not sure what that one was. Nothing. A little wiggly electron in the left-hand side there. So sometimes, oh, that was quite a nice one. That looked like another electron there. So sometimes they show up very clearly. Sometimes you seem to have to wait for ages for a couple of good ones to come along. Yep, that's indeed the case. So that's why I made this video, just in case it wasn't particularly convincing in a live demonstration. It's always good to have a Blue Peter, here's what I made earlier sort of thing. So in fact, when you think about detectors, when it comes to, for instance, even the Large Hadron Collider, where they build a really big, sophisticated electronic detector, before they switch the accelerator on, they still switch the detector on and see if they can see cosmic rays. Because cosmic rays are always there, and therefore there's a way of calibrating their detector because they know pretty much what cosmic rays they're expecting to see, and then they switch the accelerator on to see what they're generating with their particular accelerator. So not only cloud chambers, but cosmic rays are useful for any detector in which you're looking for fundamental subatomic particles. That is the result of adding together about an hour's worth of cosmic rays. So again, I took a video for an hour, went through it rather meticulously, and picked out all the frames that looked interesting and added them all together. So that's about 100 or maybe 150 cosmic rays. And you can see they're all different. Some are very bright and straight. They're probably protons. Some are very straight and not so bright. They're probably muons. Some are very wiggly. They're probably electrons. So you can see that if you're patient enough and if you're prepared to sit there for quite a few minutes, you will see lots and lots and lots of particles. There might even be, in this particular case, this is all cosmic rays. Every once in a while, you might see an alpha particle. Alpha particles, remember, 2 protons, 2 neutrons. They are big bulldozers, but any generated in the atmosphere won't be able to get through the glass. Alphas do not travel well through a medium. They travel through air a short distance, but they will not travel, for instance, through glass. And therefore, if you see an alpha inside the cloud chamber, it can't have come from outside the cloud chamber, because the alphas would not get through the glass. So if you do see an alpha, I haven't included any in this particular plot, but I've got a picture of one later if you want to have a look. You know that that must have come, it must have originated inside the cloud chamber. It must have come from radon. It must have come from radon gas, and radon gas is inside the cloud chamber, just like radon gas is in this room, because we know it can't be a cosmic ray. So you can, by eye, with a little bit of practice, you can start to recognize which particle it is we're looking at, just by recognizing the characteristics of the shape of the track. That's what we might do on the surface of the Earth. There are lots of cosmic ray experiments. The technology of a cloud chamber is 100 years old, but the technology of cosmic ray detectors, of course, has moved on. And the 1970s saw cosmic ray detectors attached to Voyager 1 and Voyager 2. There's the cosmic ray detector on the Voyager boom there. They were flown on the Voyagers, partly to see what's out there. If you fly through the solar system, what sort of cosmic rays do you see? Do you see a greater flux when you get close to a planet? Does Jupiter have any more cosmic rays coming from it compared to the Sun, compared to the interplanetary space? In 2012, Voyager 1 measured a significant jump in cosmic rays. In other words, it saw that the number of cosmic rays that appeared to be coming from the Sun, the low energy stuff, went down, and the number that seemed to be coming from outside the solar system went up. In other words, it was said that in 2012, that's the point at which Voyager 1 left the solar system, because there was an abrupt change in the number of cosmic rays that it could see. Voyager 2 is traveling about 10% slower. They were launched at the same time, give or take a few weeks, but Voyager 2 is traveling more slowly. Remember, Voyager 2 is the one that went not just to Jupiter and Saturn, but also Uranus and Neptune thereafter, and Neptune slowed it down a bit. So Voyager 2 is traveling more slowly, which means Voyager 2 didn't leave the solar system until 2018. And if we see what it actually recorded, this is as a function of time during 2018. The bottom trace is the low energy stuff, the things that we think might be coming from the Sun. Notice that it suddenly takes a nosedive at roughly the same time as the high energy stuff, the top line, which starts to increase quite dramatically and again has a little bit of a step. So it was determined that that particular point there in November 2018 is the point at which Voyager 2 left the solar system. That was part of the definition of saying that's when it's left the influence of the sun, when the cosmic rays that aren't anything to do with the sun suddenly took an increase. There are cosmic ray experiments on the space station. There it is in the bottom right-hand side. AMS stands for Alpha Magnetic Spectrometer. You can see roughly how big it is from the astronaut that's on the top left there. It's a big detector that's been sitting on the space station for years, and they are recording what is hitting that spectrometer, that particular detector. And of course, this is before they've arrived at the atmosphere. So detectors like this are telling us what the Earth is receiving at the top of the atmosphere. In addition, we want to know what makes it to ground level. So there are various detectors scattered over the surface of the Earth. There's a few really big observatories dotted around the Earth. One of the biggest is in Argentina. It's called the Pierre Auger Observatory. And the artist's impression on the right-hand side says if a particle comes in and produces an air shower, then when that air shower reaches ground level, can we detect what's going on? And these detectors are spread over a relatively large area. Each of these little detectors there, shown on the right-hand side, is a sort of a tank, if you like, a water tank. And to make sure that you've got a reasonably big footprint, these are spread over the area of Luxembourg. So you've got plenty of open spaces in Argentina, and they've used a huge number of square kilometers with lots of these detectors to try and detect particles traveling through. If no one's there to see it, cloud chambers are great if you are there to watch or to photograph. How do these detectors tell whether a cosmic ray particle has passed through this big tank of water? They're using a particular phenomena called Cherenkov radiation. And the easiest way of visualizing what we mean by that is to think of an analog. What happens when an object, such as a fighter jet, moves through the air faster than sound can move through the air? In other words, what happens when a plane moves faster than sound? If an object moves through the air faster than sound can move through the air, you end up with a sonic boom. You end up with a shock wave, which is seen by where this water is changing its phase here. So you end up with a shock wave if you travel faster than sound can effectively move the air out of the way. That's the sonic version of a shock wave. But there is a photonic version. There is a light version. If you can travel through a medium faster than light can travel through that same medium, nothing can travel faster than light in a vacuum. But if you're traveling through water, light is slowed down, which means it's possible for a particle to travel through a water tank faster than light can travel through that water tank. And then you get the equivalent, the photonic equivalent of a sonic boom. And this indicates what's going on. If a particle comes in, it produces an air shower, a cascade of high-energy particles. The particles are moving faster than light in the air or water. And just like an aircraft produces a sonic boom, the particles, if they're fast enough, can produce a photonic boom, Cherenkov light. You get a blue glow from all the particles that are traveling through either air or water. This particular video is based on a telescope which is looking at the particles traveling through the air, one in the Atacama Desert and the other in La Palma. There's two sets of telescopes looking for this characteristic blue flash of particles traveling through the air faster than light can travel through the air. So there's a whole load of telescopes being built on the Canary Islands, a whole load of telescopes being built in the Atacama Desert, and they are looking at the sky, not looking for particular objects. They are looking into the sky for the blue flash of particles traveling through the air faster than light can travel through the air. The same for those water tanks that we were looking at in the Pierre Auger Observatory. There are photodetectors inside. If they see a blue flash, that means a particle has passed through, traveling very fast, very energetic. You can do it with water. You can do it with air. You can do it with water not as a liquid. You can do it with water that is in the ice phase. So the Ice Cube Laboratory, the laboratory is at the top there, on the top of the ice pack of Antarctica. There's the Antarctic bedrock at the bottom, and on the left-hand side, there's the Empire State Building just for scale. What they've done is go to the ice cap of Antarctica, drill down into the ice cap and thread it with a whole load of photodetectors, effectively like a string of pearls. You put a few thousand of those down into the ice so that you then have effectively instrumented a huge block of ice to look for any particles that's traveling through the ice. They've instrumented 1 kilometer by 1 kilometer by 1 kilometer of ice. It's the biggest ice cube in the world. It's 1 kilometer cubed. That's why it's called the Ice Cube Laboratory. So they have thousands upon thousands of these little sort of basketball-sized photodetectors, and they're looking for the blue flash so that if a particle comes in and travels through the ice, it will produce a blue flash, and then they're looking for how many detectors see that blue flash. And if they figure out which detectors saw the blue flash, they can figure out where did this particle come from. They can just use geometry to say, well, if these detectors saw the blue and these detectors didn't see the blue, it must have come from that direction. So with enough data, you can start to trace back where these things have come from. And that's the final part of this talk. Where did they come from? Where did they come from, and how did they get so much energy that they can dump a lot of it into the Earth's atmosphere? Just as a reminder, 100 years ago, give or take a month, November 2024, I think it was, yes, November 2024 was the point at which Hubble said, look, if you look at variable stars in the Andromeda Nebula, or the Andromeda Spiral as it was called at the time, or the M33 Triangulum Spiral, these variable stars tell us that these objects are not in our Milky Way. They are galaxies in their own right. Almost overnight, the universe got an awful lot bigger, because up to this point, we didn't know whether the entire universe was just the Milky Way, with some odd-looking objects in it. But now we know some of those odd-looking objects are not inside the Milky Way. They are galaxies in their own right, at least millions of light years distant. So that was the nail in the coffin of the so-called Great Debate that took place in the 1920s, when they were trying to figure out what are these nebula we see in the sky. We now know that we can see 1 trillion or so other galaxies. And that's relevant because if we're talking about trying to work out where cosmic rays come from, originally we said, well, cosmic rays don't appear to come from the sun, they come from somewhere more remote. But the question was, well, where in the Milky Way do they come from? But now Hubble has told us, as of the 1920s, Hubble has told us the universe is much bigger than just the Milky Way. There's billions, if not trillions, of other galaxies out there. So in a sense, you can rephrase the question. Do cosmic rays come from our galaxy? Are they galactic? Or do they come from other galaxies? Are they extragalactic? That is now the question that we need to answer. And the simple answer, spoiler alert, is we're not actually too sure. We think very energetic sources might be, for instance, the shock wave produced by a supernova might accelerate particles up to very high energies. Maybe supermassive black holes and the jets formed and the shock waves formed in the jets around supermassive black holes might also be a source of very energetic cosmic rays. I'm not going to explain this on the right-hand side because we're not even sure if it's right or not. It's just a hypothesis that maybe shock waves can pass through a bunch of charged particles and accelerate those charged particles up to very high energies. So theorists are trying to work out how that might happen. So the best candidates we've got at the moment are possibly shock waves from supernova or shock waves from supermassive black hole jets. But we're not entirely sure. But shouldn't that be easy to figure out? Remember, we've said that if a particle passes through one of these water tanks or ice tanks or air, we can basically look for the blue flash and see where this particle came from. So can't we just sort of measure the directions of incoming cosmic rays and trace back to where they come from and see what's there? Well, in principle, yes, but no, it's not so simple, unfortunately, because we're talking about charged particles. Generally speaking, protons and maybe alpha particles, they're charged so they bend or get deflected in magnetic fields. And unfortunately, as best we can tell, magnetic fields are everywhere. So for instance, we know the Earth is surrounded by a magnetic field, which is why it protects us to some extent. Some particles get caught in the Earth's magnetic field, and particles don't just rain down on the Earth, they get caught by the magnetic field and spiral along the lines. Occasionally that happens and we end up with aurora, but some particles definitely get through the Earth's magnetic field. So just like we can map out a magnetic field by sprinkling iron filings on a magnet, how can we work out what magnetic fields exist in the Milky Way? Well, luckily enough, we can use dust to do that, because dust particles will also tend to line themselves up with magnetic fields. And we can detect the existence and orientation of dust by using the polarization of light. So experiments done by existing satellites have already given us some indication of what the magnetic field looks like in the Milky Way. And the answer is it's a mess. It's really complicated compared to for instance, the magnetic field of the Earth. And don't get me started on what's going on between galaxies. We have no real way of figuring out what is the magnetic field between us and Andromeda, or between Andromeda and another galaxy, because we don't have enough data to figure out what these magnetic fields are. So if charged particles bend in a magnetic field and we don't know what the magnetic fields are, how can we possibly trace back where that cosmic ray actually came from? That's the tricky thing. We assume, because we understand the laws of physics, that if the particle is really energetic, then it should sort of go in a straightish line. The less energetic ones will tend to deviate and be scrambled by the magnetic field, but hopefully the really energetic stuff should travel in a straight line. So all we have to do is to make sure we pick out the cosmic rays which are really energetic, and then we'll be able to trace back and see where they came from. Just as an idea of energy, low energy stuff like the visible light in the cloud chamber, or the visible light that's coming from the TV screen, that has an energy. I'm going to use these units without talking about why we use these units, but a unit of energy is called an EV, and the visible light that we're referring to here has an energy of 1-ish EV. So let's just treat that as the energy of a visible light photon. 1,000 times higher is more energetic, that's X-rays. 1,000,000 times higher, that's the sort of energy of alpha and beta and gamma radiation from radioactive samples, for instance. But if we go to 1 billion or 1 trillion or 1 quadrillion or 1 septillion times higher, now we're in the range of cosmic rays. You can see we're talking about humongous energies compared to the energies of particles we're used to. And just for context, the Large Hadron Collider, or the next generation, if they get enough money to build one, the Future Circular Collider, those arrows tell you where the energies are for those particular things. You can see that the energy of cosmic rays is way bigger than the sorts of energies we can generate in our particle accelerators. And the colors don't look fantastic here, but we think the lower energy stuff is coming from the sun, the middle energy stuff is coming from the galaxy, and the really high energy stuff is coming from outside the galaxy. And the red line tells us how many we could expect. The low energy stuff, we might get 1 every square meter of the Earth's surface per second, or at least the top of the atmosphere. But the more energetic stuff, we're going to have a lower flux, 1 per square meter per year. Not many of these come in. And the really high energy stuff, 1 per kilometer square per year. So we're not likely to get many of those particles raining down on us, the so-called ultra-high energy cosmic rays. But we have seen some of these things. For instance, back in the Astronomy Picture of the Day, December 2023, they published this data from the telescope array in Utah, where they saw a very energetic incoming particle called the either Amaterasu or Amaterasu, depending on how you pronounce it, Japanese sun god. Roughly translated means shining from heaven. Something very energetic came into the Earth's atmosphere, and when it was calculated how much energy it had dumped into the array on the ground, they found it difficult to believe just how much energy that was. It was an absolutely humongous amount of energy for a single individual particle. Let's be clear that the Amaterasu event should not be confused with the tiramisu event, which is how they celebrated the discovery of this particular incoming particle. But they figured that, you know, this is so energetic, it ought to be possible to trace back. So if you trace back the direction of this incoming thing, then you should be able to figure out, well, did it come from a supernova or did it come from a distant galaxy? So this is what they did. And the direction they found pointed to, pause for dramatic effect, nothing. They couldn't figure out. It didn't seem to come from a supernova. It didn't seem to come from a distant galaxy. So there was no obvious source for this very energetic particle. No supernova, no black holes could be identified. So the bottom line is we need to do more research. We need more data to figure out where these things are coming from. And let me finish by saying just how energetic some of these particles are. The more energetic a particle is, the closer it's traveling to the speed of light in a vacuum. Remember, we're not talking about going through water or anything else. Speed of light in a vacuum. The most energetic particle seen a few years back was called the oh my god particle, because when it was seen, they literally could not figure out how any object could possibly gain that much energy. But they calculated how fast it was moving. And energy can be used to calculate speed. And the speed, expressed as a fraction of the speed of light, as a percentage of the speed of light, it was 99.999999. We're not done yet. 999. Still not done yet. 999. We're not there yet. 999. We're nearly there. 995% of the speed of light. That's its speed. And again, trying to work out how, where did it get that much energy from to travel at that speed? And because it's difficult, it's always difficult in astronomy to get a head around these numbers, there's just one thing we can do to visualize just how fast this is, how close to the speed of light this is. Imagine a race between that particle and a light beam. Well, we know the particle is traveling slower than light. So let's have a race that's long enough so we can see the difference. Let's have a race which is a racetrack of 100,000 light years. In other words, we're going to race across the galaxy. We're going to race across a perfect vacuum, but the scale of that race, the start and finish line, are separated by 100,000 light years. They start at exactly the same time. Now, of course, light will win. The cosmic ray cannot travel faster than light, so light will win. But by how much? When the light crosses the finish line, how far behind it is the cosmic ray? Is it going to be a light year behind or 1,000 miles behind? When the light crosses the finish line, the cosmic ray will be behind it by 5 millimeters. After a race of 100,000 light years across the galaxy, it will have only lost ground to the effect of 5 millimeters. If you're thinking about it in terms of a stopwatch, a race that lasts 100,000 years, what's the time difference between light crossing the finishing line and the cosmic ray crossing the finishing line? It is way less than a nanosecond. It is only a few trillionths of a second, a few picoseconds, much, much less than a nanosecond. And that sort of puts it into some scale as to just how fast these things are going. So I've already gone way over my time, so let me summarize. Cosmic rays, the particles are accelerated somewhere, somehow, and we don't know where and we don't know how. We think supernova and supermassive black holes are probably involved, but we don't actually have any evidence that backs that up. That's just theory as of yet. A hypothesis that shock waves might produce that. We know that cosmic rays are deflected by magnetic fields. The lower energy particles will get their path scrambled. We hope that the really high energy stuff will travel in close to straight lines, and that will help us identify the origin. A number of particles make it past Earth's protective magnetic field. They hit the atmosphere, produce an air shower, and the air shower of secondary particles, many of which make it to ground level. And they include muons, electrons, and protons, and they make clicks in Geiger counters, and they leave tracks in cloud chambers. So that's a reminder of what a cloud chamber can show you. Lots of different particles arriving. And I've switched the Geiger counter back on to remind us that each click you can hear is a cosmic ray particle. So each click signals the arrival of a particle that might have started its journey in a supernova somewhere in our galaxy, or possibly in a black hole in another galaxy. So in a sense, when you listen to the clicks, you're listening to the universe. Thank you for listening.